For the next several videos, we're going to be taking a look at what's known as implicit differentiation. Specifically, what we want to get out of here is distinguish between functions that are written both implicitly and in explicit form. We're used to the explicit form. We need to introduce this idea of an implicit form. And of course, we want to use implicit differentiation to actually find the derivative of a function that's written in implicit form. So let's take a look at a couple of examples here of functions that are explicit. If I were to say y equals 3x plus 1, this is an explicit function. Y is written explicitly in terms of x. F of x equals sine x. Again, we think of f of x as actually being y. So again, y is written explicitly in terms of x. And likewise, y equals 1 over x. Now, these first two, if I were to take this one and I were simply to write this as y minus 3x plus 1, you'd recognize that as being the same linear function. It's just in a different form. Well, this form is, in fact, the implicit form of this linear function. Likewise here, y equals 1 over x. I could write this as x times y equals 1. This is an implicit form of this function. These two functions are actually identical, just one is an implicit form of the other. So now consider the following implicit functions, yes, written implicitly. It would be a simple matter to solve it for y, giving us an explicit function for which we can easily find the derivative. Well, kind of. If I do that, if I solve this for y, what I get is y squared equals 9 minus x squared. So that means that y equals plus and minus the square root of 9 minus x squared. So what I end up with in this particular case is actually two different functions. The reason being that this is actually not a function to begin with. If you recall, this is a circle, and where the radius here, this is the radius squared, so the radius is actually equal to 3. So if I were to graph this thing, this would be negative 3, 3, 3, negative 3. A circle is what this thing looks like. And as you recall from algebra, the vertical line test, it fails the vertical line test miserably. This is not a function by the definition of a function. But I could break this up and look at, say, this half, and then look at this half, which is exactly what this does. But I'm still in a situation where I'm dealing with two different functions. Implicit differentiation is really nothing more than an application of the chain rule. So let's take a look at this previous example, and I want to take the derivative with respect to x. Now I'm going to think of y as being a function of x. So I have this thing x squared plus y squared equals 9. But I'm thinking y as a function of x. And just for notation, I'm going to call it u of x. You could call it f of x if you want. It doesn't really matter. So this would then become x squared plus u of x squared equals 9. So y is an implicit function of x. Now if I take the derivative of both sides, I'll have d dx of x squared plus d dx of u of x squared equals d dx of 9. Well, with respect to x, the derivative of x squared is 2x plus, this apply the chain rule here. This would be 2 times u of x to the first power, which I really don't need to write, times the derivative of u of x, so u prime of x, which is equal to 0, because the derivative of the constant function is in fact 0. So this u of x is actually y, and this is actually y prime. So I can actually think of this in terms of 2x plus 2y y prime equals 0. So now all I really need to do is solve this for y prime, because y prime is dy dx. And when I do, I'll get y prime is going to equal, see, I'll have a negative 2x divided by 2y. The 2's that cancel out. This is negative x over y. So y prime, which is dy dx, is equal to a negative x over y. What this is saying is we need both the x and the y coordinate to find the slope of the tangent line at that point. Well, back here we had two functions, and it makes sense if I have an x, say, right here. If I'm looking for the slope of the tangent line, say right there, well, I need to know these coordinates because this x has two different y's. That's the result of this. So I really have two different slopes going on. So if I use the positive function, I'll have the slope up here. If I use the negative of this, I'll have the slope down here. Or actually the other way around. Or is it that way? No, wait a minute. I think it's the other way around. Okay, I think you kind of get my point here. How would we know for sure? We have to really think about this. Just because this is negative, I guess that means I want the negative of it. But using these two functions just give me a headache already. But if I know the coordinates here, that's all I need, because this is going to have a different x and y coordinate. If I know the coordinates down here, then that's all I need, because this is, whoops, went back one too many, sorry about that, there we go, because this will have the x, y coordinates that we need to put in there that will give us the slope for the point that we're actually talking about.